Right, so QR factorization, this completes, or what would, well, I'm not going to say it completes linear algebra. Linear algebra is a massive subject. You could do a whole degree on linear algebra in itself, but this completes the linear algebra part for this unit. Okay, so up until now, we've looked at direct methods, which include LU factorization, Cholesky, and we've also looked at indirect methods, for example, Jacobi, Gauss-Seidel, and SOR. Today, we're going to be looking at QR factorization, which is a return to the direct methods. QR is quite useful because it can be used to solve what we call overdetermined systems. Okay, so up until now, we've been dealing with systems which have the same amount of equations as unknowns. So if a solution exists, it's going to be a unique solution. Overdetermined systems are ones where you've got more equations than you have unknowns. So that's what we use QR for, or we can use QR for. Because we've got more equations than unknowns, an exact solution does not exist for an overdetermined system. The reason being, if the exact solution did exist, one of those equations would be just a linear combination of the other equation. Okay, so if you can't simplify your set of equations down anymore, and you've got more equations than unknowns, you don't have an exact solution. But what we can do is we can get a solution which most closely agrees with the system. So that's what we're going to be looking at today. And how we're going to be looking at that is a thing called linear least squares, which you may have met in statistics, for example. Regression is the least squares technique. Okay, so this is what we're going to do with least squares. This is also useful if you happen to do a project involving satellite navigation. Is the saber here? Where are you? Pay attention. Okay, sorry, that was just for one student there. But okay, residual vector. Just to remind you, we looked at this last week. The residual is simply your right-hand side vector b. So if you've got a system which is a times x equals b, your residual vector is your right-hand side b minus your coefficient matrix a times x. X is your current, well, x is a solution. Last week, using indirect methods, x was our current estimate. X is just a solution. And what we saw is we can look at the norm of the value of r and measure how close the solution is to the actual solution. Okay, smaller r is, the better. The closer x is to the actual solution, if it exists. Okay, well, a linear least squares problem is used for overdetermined systems. Okay, where you haven't got an exact solution, but we want to get the best solution, the one which most closely satisfies the system of equations. It's not even. Don't think of the residual as an actual error. It's just a measure of how close you are. So it's not an error. So it's like it's a measure of how close you are. That's the best way I can think of to describe it. Okay, the linear least squares problem. Okay, if you have an overdetermined system, you're looking for the vector x that minimizes the square of the norm. Okay, norm. If we use let's. Euclidean of the elements in the vector. So we're looking for the values of x which minimize the norm squared. That's our linear least squares problem. Okay, one way we can do this is using the normal equations. Okay, I've mentioned this in the notes in a bit more detail using some calculus, but I'm going to sort of brush over it here. We're not that interested in the normal equations, but this is one approach. Okay, so if ax equals b is an overdetermined system, the value of x which minimizes well, I'm going to say this is r squared. I know it's a norm of r squared, but just for for brevity's sake, okay, which minimizes R squared, satisfies these equations. And these are called the normal equations, and they're derived by using calculus. Okay, calculate the change in the value of the norm, whereas calculate the minimum using sort of maxima and minima theory, and we get this. So these are the normal equations. So A transpose X, A transpose times A times X is equal to A transpose times B. Well, from our work in Cholesky factorization, we know that A transpose A is positive definite. So therefore, we can use Cholesky. Brilliant. We could already solve that. Might as well go home now. We've solved the normal equations. Unfortunately, one thing I haven't mentioned before is normal equations are prone to inaccuracies. Okay, so for some, I'm not going to do an analysis of this, but for some values, these are notoriously inaccurate. So you start to use them, and the results you get out are bear no resemblance to a sort of usable solution. So we don't use, or we don't tend to use Cholesky for this reason. Okay, what we do use is QR, and QR factorization is a factorization like LU. So we want to come up with two matrices that, when multiplied together, give us the coefficient matrix. QR factor Q and R, well, actually, matrix Q is an orthogonal matrix. Okay, so the definition of an orthogonal matrix is where each column of your matrix is what we call an orthonormal vector. Orthonormal vectors are vectors which are normalized, okay, so magnitude of 1, and they're orthogonal to each other. Okay, so orthogonal. The easy way to test for orthogonal matrix is you multiply A transpose. If A is a matrix, if A is an orthogonal matrix, rather, A transpose times A will give you the identity matrix. Dead easy to test for. If that's the case, any matrix times A that gives you the identity matrix, that matrix must be the inverse of A. So alternatively, if you know what the inverse of A is, that should equal A transpose. That's not as useful because obviously calculating an inverse of a matrix is quite expensive. So we just tend to multiply. If you suspect A is orthogonal, transpose it, multiply it by itself, you should get the identity. And there's a simple example there. You right? Sorry, just counted. Okay, so here we have a 2 by 2. Okay, so if we evaluate A transpose times A, transpose A, and we get the identity matrix. Furthermore, if you calculate the magnitude of the columns, you get a 1. So that's an orthogonal matrix. We want one of our matrices which results in the factorization to be orthogonal, hence why we need to revisit that. Okay, we also need to know about vector projection. So this should kind of be recap to what you've done in previous studies in linear algebra. So a vector projection is a projection of one vector onto another. I tend to think of it as like the shadow cast from one vector onto the other vector. So if you look at the bottom here, we have this diagram, two vectors A and B. Okay, if I want to project A onto B, as you can see, sort of, if you sort of draw the dashed line down, okay, this works in two dimensions. Okay, we have this vector here, which points in the same direction as B, but is either slightly shorter or slightly longer. Okay, so the magnitude of this projection we can calculate using the dot product. Okay, so this is the notation I'm going to use. I don't know whether you've seen this notation before. Okay, so proj subscript B A means the projection of A onto B. Okay, I've used this notation because it's the one which is most commonly used in the literature. And we can calculate this. Again, I'm not going to show you the derivation of this, but I have given it in the notes. Okay, it's simply a dot product between A and B divided by the magnitude of B squared multiplied by B. So if B is a unit vector, that means the magnitude of B is just 1. So we've got no need for that fraction. So if that's the case, we just got A dot B, which of course gives us a number. A dot B is a scalar, multiplied by B. So this is some scalar applied to B will give us this vector here. Okay, that's vector projection. And like I mentioned, there is on page 147, there is a derivation of that if you're interested. Right, so why have I just talked about that? Okay, we're going to use vector projection to calculate an orthogonal matrix. Okay, so and we're going to do it using a method called the Gramschmidt process, which you may have, did you do that last year in linear algebra? Right. Okay, so the reason why we want to do that is we want to factorize a matrix into a product of an orthogonal matrix and an upper triangular matrix. And this is what we call QR factorization. Why is it called QR? I don't know. I'd have to look that up, but it just is. Okay, so QR factorization factorizes an n by n coefficient matrix, so it doesn't have to be square. Usually m is greater than n, because we've got an overdetermined system, into the product of two matrices, Q and R. Q is our orthogonal matrix. So every column is a vector which is orthogonal to every other column. R is an upper triangular matrix. And we can use QR to solve overdetermined systems where the number of equations is greater than the number of unknowns. For example, our linear least squares problems. We're going to look at two methods. There are actually three main methods in which which we can use. We're going to look at two of them, Gramschmidt, and later on today we're going to be looking at householder transformations. So there are two methods here. Right, the first one is the Gramschmidt process. So you sort of familiar with this in the past with previous studies, but I'll just revisit and go over it again. Okay, what we have is we have a matrix A, and what we're going to say is, right, matrix A consists of n vectors, which are all column vectors. Okay, so A1 will be a column vector, A2, column vector, etc. And we're going to assume that A's are linearly independent column vectors. Okay, so then there aren't multiples of each other. What I want to do is find a matrix U, which consists of column vectors, where U is an orthogonal set. So that means all of the U's are orthogonal to each other. So A's are not orthogonal to each other. We want to create a set of U where they are orthogonal to each other. Okay, so if we have A1 and A2 to start with, okay, so these are, I'm going to show it, sort of demonstrate it geometrically. So here we have a vector A1, okay, and a vector A2. If I've only got A1, then A1 or U1 equals A1, because U1 is orthogonal, it doesn't have to be orthogonal to anything else. So if you ignore A2 there for a second, and I've only got A1 in my setup here, okay, U1 is just equal to A1 because it doesn't have to be orthogonal to anything else. But if I have got A2, I need a vector which is going to point up this direction, which is going to be orthogonal to U1. Okay. How do I do that? Well, a couple of slides ago, we looked at projection. So if I project A2 onto U1, I get this vector. So this vector here is the projection of A2 onto U1. And what I'm going to then do is I'm going to subtract this projection from A2. Okay, so that's simply A2 minus the projection of A2 onto U1. This then gives me the vector U1. Okay, so if I have a vector going from this point up to this point, well, it's going to go a bit further because it doesn't have to be a unit vector, but I'm going to get this vector. Okay, this is orthogonal to U1. So U1 and U2 are orthogonal to each other. And U2 was found by subtracting the projection of A2 onto U1 from A2. And that's a Gramschmidt process. For the next vector, we need it orthogonal to both U1 and U2. So we're going to have to subtract two projections. And we keep going on until we've gone through all our vectors in A. Okay, so a more sort of mathematical approach. So the first vector, U1, is simply equal to A1. There are no other vectors to be non-orthogonal to. U2 needs to be orthogonal to U1. So we simply subtract the projection of A2 onto U1 from A2. Now U3 needs to be orthogonal to both U1 and U2. So A3, we take A3, we subtract its projection onto U1, and we also subtract its projection onto U2. And we continue until we've done all of the A vectors. Okay. So if we have AJ, so J is just some vector A, we have a sum of the projection of AJ onto UI. And instead of, if I wanted to write it, instead of writing it as proj, okay, I could write it as that projection. With the Gramschmidt process, with QR factorization, we need our U vectors to be unit vectors. So if U vectors are unit vectors, this norm on the bottom over here, that's going to be 1. That's going to get rid of that fraction. So it simplifies things quite significantly. Okay, so I'm going to use E to denote the unit vector. And these are my columns of Q. So since E's are unit vectors, okay, we can change this expression down here, okay, to be the sum of a dot product times our unit vectors. Okay, rearrange this to make A the subject, and I've just got UJ equals plus that sum. Okay, so all I've done is rearrange to make added the sum to both sides of this equation, and then we know that UJ is equal to that projection. Okay, so therefore we can include UJ in the sum. Okay, so at the end of the day, we've significantly simplified things rather. So we've got our AJ, which is what we started with, is equal to the sum of a dot product times our unit vector. Okay, so therefore using Gram-Schmidt, we can write it as this. Given A is a load of linearly independent column vectors, okay, A1 must equal E1 dot A1 times E1. A2, okay, so we have remember we have the summation, so E1 dot A2 times E1 plus E2 dot A2 times E2, etc., etc. If that's the case, I can write that as this matrix equation. So this equation here, remember E1s are all column vectors, so this is actually a matrix, but I've written it in form of E1, multiplied by an upper triangular matrix of dot products. Those dot products are all obviously scalar values. So this is your upper triangular matrix. This is our orthogonal matrix. So this is Q, and this is R. So effectively, we've used the Gram-Schmidt process, applied the projections, and then written it in the form of a matrix equation. So that's calculating QR using Gramschmidt. And we're going to break it down into a series of steps. Okay, so let's say we're given a matrix A. We want to calculate Q and R. How do we do that? Well, to start, we let U1 equals the first column in A. And for each column in J, we calculate our Rij, which are the elements in the upper triangular matrix R, which is just a dot product. We then calculate our U vector. This U vector will be orthogonal to every other U vector. And we do that by the jth column of A minus that summation. This is your Gram-Schmidt bit. Once we've got Uj, we need to calculate its, we need to normalize Uj. So calculate its magnitude by calculating the norm, and then divide Uj by its magnitude to give us Ej. Okay. For the first column of A, we can't do these first two steps, so we just go straight to Rjj. Okay, so that's the process. And so obviously what I'm going to do now is you're quite used to my methods by now. We're going to go through an example, and we're also going to go through a worked example. It becomes a lot more clearer, as always, with examples when you do these type of things. Okay, so I'm going to calculate the QR factorization of this matrix using the Gramschmidt process. Okay, this matrix happens to be 3 by 3. We can still apply it. We can still calculate the Q and R, but we could also do it if it was 4 by 3, 5 by 3, etc. Okay, the first column, we let U1 equals A1. So A1 would be the vector 12, 6, minus 4. And our first element in our upper triangular matrix R is simply the norm of U1. So calculate the Euclidean norm, 12 squared plus 6 squared plus 4 squared, root 196 gives us 14. Okay, then we need to normalize our A1, which happens to be U1. So we normalize U1. So we divide the first column by R11. Okay, so this is our unit vector. And of course, it's orthogonal to itself. I mean, it doesn't have to be orthogonal to anything else. Okay, it's just a unit vector. So essentially, the first step is to calculate the unit vector of the first column. Okay, second column. This is where we have to step through all 4 bullet points in that process. So second column, we've got to calculate R12. This is just a dot product between E1 dot A2. So if you remember EA, EI, AJ. So E1 dot A2. So E1 we just calculated, which is this vector here. A2 is our second column of A. So second column is minus 51, 167, and 24. Okay, calculate the dot product, we get 21. Now we have to apply the Gram-Schmidt process to calculate a vector which is orthogonal to E1. So we take A2 and we subtract R12, which is 21, multiplied by E1. So we want to find an orthogonal vector to E1. And this is Gram-Schmidt. Okay, so what have I done here? Well, 21 divided by 3 is 3, so that gets rid of the 7 denominators. Okay, and this leaves us with this vector here. Okay, this is our U2. So this vector is orthogonal to that vector there. But we need a unit vector, so we normalize it, but calculate the norm of U2, which gives us our R22, which happens to be 175. Okay, and divide U2 by R22, giving us E2. So this is a normal vector, which is orthogonal to E1. Third column. So we need dot products to calculate R13 and R23. So E1.A3 gives us, A3 by the way is the third column of A, gives us minus 14. E2.A3 gives us minus 70. So once we've got your R13 and R23, we can then apply Gramschmidt to calculate U3. So U3 has to be a vector that's orthogonal both to E1 and to E2. So Gramschmidt, take A3, subtract the bit which is non-orthogonal to E1, and also subtract the bit which is non-orthogonal to E2. If you do that, you get this vector here, which is U3. Okay, we need this to be a unit vector. So again, if we calculate its magnitude, R33, nice numbers, happens to come out at 35. That's sort of, that's, by the way, doing this in practice, you'll never get nice numbers like this. I've deliberately used a matrix where it does give you nice numbers. So R33 is 35. Divide our U3 by 35, and we get this. Okay, so we've now got all of our elements of our upper triangular matrix R, and we've got all of our columns of our orthogonal matrix Q. So we just put them together. So the matrix on the left is simply your E1, E2, E3. Those are all unit vectors, and they're all orthogonal to each other. So that's our orthogonal matrix. And this matrix on the right is our upper triangular R matrix. And if you multiply those two together, you get back to your A. Okay, so it's a lot more involved than perhaps LU factorization. But this can also be done where you have more rows and columns, and it can also be used to solve those normal equations. Okay, so that's an example which is given in the notes. And just to go through a worked example as well, so just to sort of give you some practice. Okay, and probably should stress at this point, but these numbers have been deliberately chosen to give us nice arithmetic. In practice, you don't normally get nice arithmetic because there are things like square roots floating around and things like that. Okay, so this is the worked example. Notice in this example, we got more rows than columns. So we couldn't use LU factorization on this or anything like that, but we can calculate QR factorization. Okay. In a similar fashion to all of the other direct methods we're doing, we take things at each column at a time. So kind of similar to Kraut's. Okay, the first column is dead easy. U2, oh, sorry. Let's say it's easy, go wrong straight away. U1 is equal to A1. Okay, so our first vector is simply the first column of A. So that means that R11 is equal to the magnitude of 1. So what we've got magnitude of 9 squared is 81 plus 12 squared 144. Which is, oh, that's good news. It's root 225, which is 15. I was worried then for a sec. I thought I hadn't chosen such nice numbers. Okay, so I've calculated the magnitude of that first column vector. So this means if I normalize U1, we get 1 over 15 times the first column. So that will be 3/5 and 4/5, 0, 0. So essentially, your first E vector is the normalized first column of A. But the magnitude of the first column gives us our R value, our R11 value. So first column is dead easy. Okay, second column we have to apply Gramschmidt. Okay, so when J is 2, we need to calculate R12. This is just E1.A2. So E1 we just calculated, and A2 is the second column of A. So we have 3/5, 4/5, 0, 0, dot 0, 0, 4 minus 3. And you can see here 3/5 times 0 is 0, 4/5 times 0 is 0, and these are going to be 0 as well. So R12 is simply 0. What does that tell us about A2? Sorry, somebody said it. Yeah, it's already orthogonal. If all of your R values for the second, which you're going to multiply by the E values are 0, it's already orthogonal. So your U2 is equal to A2 minus R12 E1. This is your Gramschmidt. Now this second term is just 0. So U2 is simply A2. So it's going to be 0, 0, 4 minus 3. R22 is the magnitude of U2. So what we've got 16 plus 9, it's going to be 5. Okay, so the magnitude of U2 is 5. So therefore, your E2 is going to be 1/5 of 0, 0, 4 and minus 3, which I'll write in like that. Okay, so the process is you calculate the R values up to the one the main on the main diagonal. Then apply Gramschmidt to calculate your U vector. Normalize the U vector. That gives you your R value on the main diagonal, and it also gives you your unit vector E. Okay, the third column. Okay, so in this case, we've got R13, which is E1.A3. Now, E1 was 3/5, 4/5, 0, 0, dot, and the third column, 26, minus 7, 4, and minus 3. Okay, and just doing that in my head, I think that's equal to 10. By the way, I didn't do that in my head. I don't think I did. So 3/5 times 26 plus 4/5 times minus 7. So what have we got? You got 78 minus 28. Okay, divided by 5. Yeah, so that's 50 divided by 5 gives us 10. Okay, and we also do the same for R23. So it's E2.A3. So E2 was 0, 0, 4/5 minus 3/5. And we have the 26 minus 7, 4 minus 3. So 4, so it's going to be 16 minus 9, which gives us, 16 plus 9, which gives us 25 divided by 5, gives you 5. Okay, so that's the upper triangular elements done. Okay, we can't do it R33 because we haven't calculated U3 yet. So we need Gramschmidt to calculate U3. So U3 is A3 minus whatever the non-orthogonal bits from the other vectors. So minus R13 times E1 minus R23 times E2. So what's A3? A3 is 26 minus 7, 4 minus 3. Okay, minus 10 times E1. Well, E1 is 3/5, 4/5. So 10 times this is going to be 6 and 8. Actually, I'd better write it out in 4. So 10 times E1, which is 3/5, 4/5, 0, 0, minus 5 times E2, which is 0, 0, 4/5, minus 3/5. Okay, 26, 3/5 times 10, that's going to be 6, so it's 26 minus 6 is 20. Okay, minus 7 minus, well, 10 times 4/5 is going to be 8, so minus 7 minus 8 is minus 15. 4 minus 4 is 0, minus 3 minus minus 3 is 0. So that's our U3. Okay. So therefore R33 is simply the magnitude of U3. So it's the square root of 400 plus 225, which is the root 625, which of course is 25. Okay, so if we normalize U3, we have 1 over 25 times 20 minus 15, 0, 0, which is 4/5 minus 3/5, 0, 0. Okay, sorry, I'm running out of space here, hence why I'm squashing things up a bit. Okay, so now we have all our upper triangular elements R, and we have our 3 orthogonal unit vectors E1, E2, and E3. So we put them together. So Q is E1, E2, and E3. So E1 was 3/5, 4/5, 0, 0. E2 was 0, 0, 4/5, minus 3/5. And finally, E3 was 4/5, minus 3/5, 0, 0. That's our Q matrix. Our R matrix. Okay, well, R, if we look at the page, obviously I'm not going to scroll, can't scroll down, but R11 was 15, and we have 0 as the lower triangular elements. R12 was 0, R22 was 5, and we have a 0 underneath it, and R13 was 10, R23 was 5, and R33 was 25. Okay, so we now found Q and R. And that's a Gramschmidt process. So it's kind of one, if you just follow the process. Do you want me to? If you follow the process, it's kind of like quite methodical. But the point being is you're subtracting the non-orthogonal bits from all the vectors that's come before it. So your first vector, that's fine. Your second vector, well, we've got to subtract the bits which are non-orthogonal to the first vector. The third vector, you've got to subtract the bits which are non-orthogonal to the other two, and etc. And what I'm going to do in a minute is just to multiply these two matrices together to see if we get A, which hopefully we should. I'll put this up again at the end. I'm just going to switch over now to the PC to test whether we've got the right answer. Okay, hopefully MATLAB's loaded up now. It has. So what I'm going to do is I'm going to enter my Q and R matrices into MATLAB. That's my Q matrix. And I'm going to also put in the R matrix. Oh, 15. Okay, Q times R gives us our original matrix back. So we've got a factorization. Also, if I do Q transpose times Q, I get identity matrix. So the Q times R just shows us, yes, we have a factorization. Okay, the Q transpose times Q shows us that Q is orthogonal. And the beauty of orthogonal matrices is that their inverse is equal to their transpose. So if I go inverse of Q, oh, of course, it must be square. Yeah, inverse, yeah. So that only applies to square matrices. Sorry about that. Ignore that bit and just focus on that good bit rather than the bit which I just paused up. Okay, as we'll see in the second lecture, there is not a unique QR factorization. There is another method which we can use, which will give us a different QR factorization. So, for example, if I'm going to reproduce my matrix A, and I'm going to use MATLAB's QR function just to give me the QR factorization of A. Okay, if you notice here, it's given us a 4x4 Q. Well, using Gramschmidt, we only had a 4x3. This is still a valid QR factorization. Q times R gives us A back. Okay, so your Q and R aren't unique. Depending on which method you use, you'll get a different, or you may get a different values. Okay, and in the second half, we'll look at that other method.